This is the last one before Christmas. There'll be 3 afterwards, which are all on electronic noise. But I want to wrap up our discussion of op-amps with frequency-dependent feedback today. So, we will really be discussing things which they're essentially only a slight extension of 118, plus a little bit of 117 thrown in. So, could you all close your eyes? Close your eyes. I'm not going to throw biscuits at you, although it'd be tempting. So, now all the eyes are closed, even you. If you feel uncomfortable with the idea of getting the transfer function from the circuit, will you raise your hand? If you think it's easy, can you raise your hand? If you think this is a bloody stupid idea, can you raise your hand? Suit yourself. Well, if you aren't comfortable with it, I'm going to go a little bit slowly and probably do more maths than you're used to, just because I think it's important. If I give you a piece of paper, it involves you actually bothering to read it, whereas if I put it in front of you and you're not on your phone, there's a half chance that you see it at least once. On the other hand, if it's fine, feel free to go to sleep or read the paper or whatever. So we will be discussing op-amps, and I want to talk about pole zero circuits. So it's a circuit with one pole and one zero. And this pole and this zero will be created by the feedback. We will assume the op-amp is perfect. Alternatively, I could produce a circuit with a zero in it and use the op-amp's one pole to give me the pole zero. But I am not discussing that. It's just something which is possible. But before we get on to the pole zero properly, I want to talk about some first order low pass and high pass op-amp circuits, which is really just an extension of 118 to put in some frequency dependent components. And then we do some standard form type stuff at the end. So the pole zero circuit aims to adjust the magnitude and the phase of an electronic system by inserting an amplifier. The amplifier doesn't necessarily have to have a gain more than one, but usually you would not decide to have no gain, because you'll put some noise in your system anyway by adding an extra op-amp, and if you don't add any gain, then you'll make a signal to noise worse. But we will talk about that later. So usually you'll put some gain in. And there are 2 structures, and the structures were familiar. This is inverting and this is non-inverting. And oftentimes you will only put capacitors in along with resistors. You will not put in inductors. They're really very imperfect actually. They have a lot of winding resistance, especially if you want a decent size, like a big inductance to carry even a small current. You have lots and lots of turns of quite fine wire. You want a fine wire because if you use a fat wire, it takes up a lot more space. And you have to have a bigger piece of magnetic stuff to contain all that fat wire. So you want a thin wire which ups your resistance, which makes your inductor look like L plus R rather than just L. So generally speaking, you chuck out inductors. Also, inductors, when you wind them, you wind the turns next to each other, and there's a bit of capacitance between each winding because the windings are insulated with enamel, it's like nail varnish. So you have L and R in series with lots of little capacitors all the way down in some sort of transmission line type structure. And having done the transmission line now, you've done it, right? Must have done, week 12. They're a bit messy at times, which is being nice about it. And you try to avoid any imperfections if you can. So oftentimes, if you want an inductor, you use a capacitor and put a couple of op-amps nearby to fake it into being an inductance. And the way you would do that is you need to make some impedance transformation. So essentially in the same way that a transistor can transform impedances, an op-amp can transform them as well. If you think about the Argand diagram, everybody happy with the Argand diagram? It's imaginary and real. What for you? Real. Plus real, minus real, inductive, capacitive. I've got inductance and I want to get down to capacitance. All I really need to do is shuffle around the diagram, and I can make circuits that do the shuffling for me. And you make them from op-amps if you want to read about them. You can look at a book, and usually I will quote a book because our books are very good and they've been edited and blah, 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 blah. In this case, I've put a website on because this is a really good website actually. Not because everything he says is true, although it almost always is true. It's just very good if you want to look at some circuits and think about the practicality of actually making electronics. This guy is a practicing engineer for a long time, he's a consultant now. Very worthwhile reading, especially if you're bored over Christmas. So anyway, we will use these two circuits to make some frequency dependent, essentially filters. And we have some standard forms for, is it that bad? Oh, you're just tired, I thought you were. I only have some standard forms and you and I got, I thought the two were related. Lack of sleep, eh? So we have some standard form for low pass and high pass and pole zero. And you're happy with these, right? You're happy with those two? This is familiar stuff, or not? Yes. So for low pass, we've got one pole at F0, and we've got a 1 on top. And for high pass, we've got one pole at F0, and we've also got the 1S on top, or 1 J omega. And for pole zero, we've got a 0, which is 1 plus J omega JF over F1, and a pole, which is JF over F0. And F1 and F0 are different. F0 may be bigger or smaller than F1. F0 is the pole, F1 is the 0. Why on earth did I write it that way around? It's kind of tongue twister. Usually F0 is the pole, that's why we do it. So we have, you can either do it by time constant or by omega or by F. And to get to F for omega you just do 2 pi, and to get from tau to omega you do 1 over. Yeah? Good. Why did he drag me in on week 12 for this? So, these circuits aren't the same. They don't have the same transfer function. I put them up just to give an example of a passive circuit, which is pole zero, which is low pass, and an op-amp circuit, which is low pass. And I give the transfer function. I'm not going to bother to derive them, only to say that there is a frequency independent gain, which is K, which is for this circuit it's R2 over R1 plus R2. And the way you would think about that is, if F goes to 0, XC goes to the impedance of the capacitor at 0 frequency is infinite. Want a biscuit? You're not really keeping tally, are you?
Yeah, no.
That's pathetic. Right, so F goes to 0, XC goes to infinity, no current in this pathway, potential divider of R1 and R2. You block out all this business here, we have potential divider of R1 and R2, where R2 is what gives us the output. And then we have a frequency dependent bit, which here I put as S instead of omega or tau or whatever. Sorry, omega or F. And I'm saying R1 in parallel with R2. And it's fine to leave it like this as long as you don't want to take it any further. A similarly arranged circuit for an op-amp is this one when I draw it inverting. If you draw it non-inverting, it will be different, but I leave it as a challenge for you to figure it out. So we have a frequency independent gain. XC1 goes very, very large, which means these two are no longer in parallel and only this exists. And then we have minus R2 over R1, same as from 118. Happy with how to get to that? You would sum the currents at this node and say that no current flows in there because the input impedance is very high. You would say that V plus equals V minus because the gain is infinity and AV is infinite. You're familiar with this, yeah? Or not? You want me to go again? No? Sure? If you don't like it, go and have a look at the videos from 118. It's 16 and 17 in the 2 lectures. So we would end up with this transfer function. So this one is passive and this one is active, and the main difference is that this one you can have some gain which is more than 1. This one you can never have a gain which is more than 1. That's true of all active and passive circuits. So if I was to look at the frequency and time domain response of, I did the passive one, but if you do the active one, you'll get the same looking graph, just with different numbers, according to the equations. The passive one is actually easier to make the nice graph for, because I don't have to worry about the imperfections of the op-amp, which the simulator will give me anyway. So we have a K, which is slightly less than, so this is minus a number of dB, it looks like about 2 or 3 I suppose. Depends what I pick for my values of R1 and R2. And there is a corner frequency, and I've done this normalised frequency business. So I've called this corner frequency, which is 3 dB down on whatever K was. I called it 10 to the 0, which is 1 radians per second. Now it's not, I didn't actually design the filter at 1 radian per second. or maybe I did, doesn't matter. I've scaled the axes to make it so that you can see if I go 1 decade, 2 decade, 3 decade away, how many dB reduction I get. And it doesn't matter about the exact numbers. Happy with the idea of normalising the frequency axis? Yeah? No. Don't care. Right. So we'll have some roll off, and this is 20 dB per decade because it's first order, or 6 dB per octave if you prefer. And we will find that the pole is at 45 degrees lagging phase shift, and lagging is minus. Happy? All 117 stuff. And if you look at the time domain response, we will find that it rises up to a maximum slowly, and at the time constant of the circuit, we will be 66% or 67% of the way towards the top. And at 5 time constants, I normalise this for time constant in the same way I normalise this for frequency. Happy? No happy. If anybody wants a biscuit, they can give me a good definition for time constant. Harder than you might imagine. It's more an equation. Tell me what it physically means. It's true. Just in case you didn't hear that, it's the time it takes to charge it by 0.67% of the total. But why is that particular, why is 0.67 such an interesting amount? Why didn't I pick a half? I obviously didn't get to pick this, although if I did, it would be awesome. Go on. 1 minus e to the minus 1. Correct. Have a biscuit. Since they're there anyway. E to the 1 is what says the number 2.73 blah 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 is what's important in this. And that number is what it is because that's the way the universe is. And if it was slightly different, maybe we'd all just we wouldn't be anymore. Maybe. Or maybe not. I have no idea. So the value of E is what makes it significant. So this is the step input, and this is the rise time, and this here is our K, which is 0.75, which is 0.707 is 3 dB down, so this is somewhat less than 3 dB below 0, and this is going to be about 6 dB below 0 by the time we've got the 3 dB drop. Happy? Alrighty. So if I look at some high-pass circuits, this is the simplest move to a high-pass I could make from the low pass that I already had. You might notice that some of these circuits are on problem sheets from 117, because that's where I'm stealing them from. So here we've got the C in series with R1 and R2, and essentially it's a potential divider of R2 and C1 and R1 in series. And as frequency increases, the impedance of C1 gets bigger and bigger. And if we were sharing our apples, this would get a bigger and bigger share, and this would get a smaller and smaller share until your output goes to nothing. What? Have I done that wrong?
Didn't you say increasing frequency?
Yeah.
Makes sense.
Oh yeah, sorry. I have said that wrong. Well spotted. As frequency increases, the impedance of this gets smaller and smaller. Whoops. None of you stopped me, so I think you deserve a biscuit for stopping me. I've noticed a correlation between x-axis distance from the speaker and biscuit consumption. In fact, I think it might be exponential in nature. We should do some research. How many biscuits have you had? You're in the second row.
I think they're more discreet.
More discreet than that. Righto. Piecewise linear problem. Quick. Call in whatever circuits and signals now. No, signals and systems, that's what they do about rubbish. I mean stuff. Right, so yeah, frequency increases, the impedance of C1 goes down, and we head into a situation where you have potential divider of R1 and R2. So the best you can manage is R2 over R1 plus R2, which is your K, and all this stuff makes it worse at lower frequency. When I say worse, I mean more attenuation. Similar arguments for this one. There is still a biasing current for this op-amp, even though we've said gain is infinite, we don't need the biasing current. There must be some in a real op-amp, and that will be provided by the circuit, the DC path through R2. We don't have to worry that no current can flow at DC in this pathway. There is still a method to bias the op-amp. If you don't bother with your biasing currents, you'll find that you can't turn on your differential pair properly from the anatomy bit. And if you can't turn on your differential pair properly, feedback won't work properly because the transistor won't be turned on. You won't have an op-amp, you'll have a circuit that dissipates a small amount of heat. and doesn't really perform any useful function. Your output will either be locked up at plus whatever your supply is, or locked down at whatever minus your supply is. Who's got some spare notes? There we go, good. That's all right then. So these are equivalent in the sense that they produce the same looking graph, but they are in fact not producing the same transfer function. If you want to derive these, then it's good practice. It's the same method. You'd say there is a current that flows in here and a current that flows in here, and they must be equal. And this point and this point must be at the same potential for all the same reasons we usually do. And then you would just carry on with the maths. And we'll have a look at some of the maths in a bit. But right now I'm more interested in the graph. So this is a standard high-pass first order arrangement. In this case we have a rise up to a maximum, which is K. So K is the frequency independent gain. It's not necessarily the DC gain, although if you have a low-pass system, the frequency independent gain and the DC gain will be the same thing. And if you have a high-pass system, the frequency independent gain and the gain at F is infinity, that's infinite frequency, will be the same. So K is not necessarily DC gain, but it's the bit of the gain which doesn't change the frequency. So that bit is the case. So we've got a pole here, sorry. There's some 0 at minus infinity, a pole here which flattens off this response from its rising at 20 dB per decade. And at that pole frequency we have 45 degrees leading phase shift, so no minus sign. And for a time domain response, we put a step in and we'll find that we have a value of K, which is our frequency independent gain, which in this case is 0.75, and then we have a decaying exponential back towards 0. And the pole zero circuit is just a combination of these two. It will have a high frequency gain and a low frequency gain. So it will have two Ks, if you like. And it will not really have two time constants, because you can't really count your zeros as a time constant, because only poles generate time constants. We will call the time constant of this the pole zero circuit whatever the time constant of the pole is, and we will transform the zero into the same time constant by adding it's not a fudging factor, it's a converting factor. And we will see that in some equations in a bit. But the pole zero is really just a smoosh together of these two, which is why I start with them. Any questions on this stuff? So I said it's the linear sum of high pass and low pass. If you want to think about that as superposition, that's okay, because superposition is the linear sum in a time invariant system. And we are calling this time invariant. We have exactly one pole and one zero. If you have 1 0 and 2 poles, you have a second order system. It's different. Now the pole may be at a lower or higher frequency than the zero, and you call it pole zero anyway. You don't call it zero pole. I have no idea why. It's just how it is. So in the case that I've got here, I have a low frequency K, which is 60 dB down, and I've got a high frequency K, which is about 25 dB down, and I've got 20 dB per decade in the middle, which is due to this zero. We are flat, we pass a zero, we have to start rising at 20 dB per decade. Sometime later we find a pole and we have to start falling at 20 dB per decade, but we're already rising at 20 dB per decade, so we subtract the two and we end up with 0. So that's as in nothing, not a 0, just no change. So then we flatten out again. And if you look at the phase shift, we have in the beginning no phase shift, and we find a 0, and by the time we find a 0 we have to have 45 degrees leading, and then it keeps going. It wants to get to 90, but before it can we find that this pole is in the way and we have to start bringing the phase back down, heading towards 0, and at the pole frequency we'll find it's 45, because it's essentially this bit wants to do that with the circuit. So it wants to give us 45 to 90 degrees lagging, but it's starting from a notional position up here of 90 degrees leading, so it takes us back towards 0. Happy? No happy. Alright, we'll keep going for a bit and we'll see what's what. I haven't bothered to normalise the frequency because I have to make a choice about either the pole or the zero to normalise to. So in this case I just did it with some real numbers. So there are two gains, a low frequency or DC gain where f tends to 0 and a high frequency gain where f tends to infinity, and I call them KL and KH. And if the zero frequency, which is omega 1, is less than the pole frequency, which is omega 0, then the KL must be less than KH, and the phase leads. That's to say positive between the pole and the zero. And that's the case in the last slide. Is there a mistake? No? Okay. And if the zero frequency omega 1 is bigger than the pole frequency omega 0, then KL must be bigger than KH, and the phase lags, that's to say is negative between the pole and the zero. So that's the opposite of this, where we would find that the magnitude response would look more like that, and the phase response would look like that. I didn't bother to simulate that one for you. Happy or not happy? Righto? I don't think you are happy, you're a bit too quiet. So the magnitude slope will always tend to either plus or minus 20 dB per decade because the system is first order. And the phase will always tend towards plus or minus 90 degrees depending on the pole 0 or 0 pole ordering. But we will still call the circuit pole 0, irrespective. Generally speaking, it will not make it all the way. That's to say, you will almost always have a situation where you have this bit, you never see it get to 90 and then come back down again. Because if you look at the number of orders of magnitude I've got on F here, even to get most of the way to 90, I've gone from a millihertz to 100k. There are only a few times when you want a circuit with such an enormous bandwidth, and you won't have to start worrying about microwave effects. So it's actually quite unusual to find that all the way up and then down again. Although there are some times, especially in the feedback of analog amplifiers, where you do end up with enormous bandwidths involved. But usually you'll see in a textbook drawn like that. So the standard forms are the 1 plus s tau 1 over 1 plus s tau 0 all times k. But all this gives you is a value for tau 1 and a value for tau 0. If you wanted to think about it as a low pass bolted onto a high pass, you can shuffle the terms about a bit, and I leave the shuffling to you, to get you a frequency independent k times a low pass bit. So this is your KL. You might want to write that because I didn't. And then you've got your KL again times the ratio of the time constants times your high pass bit. And your high pass bit's got tau 0 top and bottom. So all of your frequency dependent stuff is now to do with the pole time constant, or the pole frequency, and you have a converting factor in the middle, which deals with the fact that the 0 and the pole aren't at the same frequency or don't have the same time constant. This is quite useful because if you want to know what happens to the high pass and low pass bits without having to think about where the 0 is, you can do it from this bit. It can also make it easier to see what the rise time is going to be like, if you prefer. Sometimes you'll see it drawn either way. More often than not, I would use this one because I like to think in frequency domain, and only if I have to deal with some pulse circuits, maybe for line return for a CRT or something to make the scan, then you have to worry about pulses because it's a pulse. It's a system filled with pulses, and then you'll worry about rise time, fall time. But oftentimes, when you work in frequency domain, this one is the one you'll use. So the high frequency gain KH, which I put in this slide, it's that bit there, KH. It does appear in this equation, but only as this factor here in the middle, k times tau 1 upon tau 0. And k is equal to k, I did write it, k is KL. So the step response depends of the pole zero circuit depends on whether the pole comes before the zero, lower frequency, or the pole comes at higher frequency than the zero. Well, what have I got here? So if the zero frequency lower than the pole frequency, we have something broadly high pass. And if you go back to this, that's the situation on this slide. We've got something with a higher high frequency gain and a low frequency gain. So we ought to expect something that's broadly high pass, but has a DC bit as well. If on the other hand we had the other way round, we had low frequency gain higher than high frequency gain. Mind bending, isn't it? High frequency gain has a bigger magnitude. Low frequency gain has a bigger magnitude than high frequency gain. Yes. Then we would expect something that's dominantly low pass, but has some high frequency bits as well. So this is the zero before pole one, and the difference between this and a regular high pass is that in the regular high pass this would drop to zero in the end. But actually in the pole zero circuit there is a constant which I give 0.1 here because that's just the numbers I picked. And this is your KL there. And it will keep like that forever. It will not drop to zero, whereas in a high pass it would. So, for several biscuits and the esteem of your peers, I'm not sure which is more important. I think down here biscuits are very more important. Maybe up the back we have high morals. Would anyone care to say what the low frequency or the low pass version of the pole zero would look like? It's not easy. It's going to look broadly like that, or for you guys like that, but there will be something special about it. Just as this one never falls to zero, that will do something else.
Go up and then drop a little bit.
Afraid not. It's a nice idea. It has some high pass, there's some high frequency gain, which is not zero. That's the clue. So something has to happen near the edge, because all the high frequencies live in the edge. Are you familiar with, how much Fourier have you guys done? A bit. So you know that square wave is made up of lots of sines, and that the bigger frequencies tend to have more effects on the edge? Yeah? I seem very confident about this. Let's digress for a bit into some signals. It'll be fun, maybe. If I wanted to make this shape, yeah, okay, we'll put the middle there, easier. This is time and this is, I don't care, bolts, whatever. I would attempt something like, whoops, like that, and this would be my F. And clearly not quite centered, is it? But never mind. And then I'd have to have F3 would look like this. I think this would be 3F. And then I'd do 5F, which will be and then I'd put 7F as well. So the closer I get to the edge, the more high frequency. In the end you end up with a little spike. It doesn't really exist and it's got a funny name. What's the name of the spike? What? No, not ringing. It's something specific about the mathematics that doesn't actually appear in reality, it goes away. So this business with this circuit, it's got some non-zero high frequency gain. So I'm going to expect something to happen at the end. And actually, what I'll end up with is a step like this, and then I'll have a jump, and then an exponential. I'm assuming my high frequency K is 1 at the moment. If I put a high frequency K in as well, maybe it tends to there. And this will be my, KL. And this distance here will be in proportional to my KH, which is different from the standard low pass, which maybe just looks like that. So you get this step. Nobody got the biscuit. Never mind. If you want to try it in Spice, put up some simple passive pole zero circuit and you can observe the height of it. So, the majority of the rest of the time I will just do 2 examples. But I will not do the examples because there's a good chance I'll make a mistake and then I'll look stupid. And I don't want that to happen. So I've already done it, I'm just going to do it on the slides. Which is different to how I usually do it. And I don't usually like to stand up and just do maths because I don't think it has much value. But in this case, I think it does have value because if you are not confident with getting the transfer function out of the circuit, you are totally screwed. So I want you to see it at least once, just in case. So this is the one I'm going to do, which is passive pole zero. And this is what I'm going to end up with. Well, yeah, this is actually this, but this bit is the tau 1 and this bit is the tau 0. And it's important to do it in a certain order. If you don't fancy this, feel free to go to sleep or whatever. But there are some things we should know about the equation before we start. There is a k in the front, which is R2 over R1 plus R2, and it has no frequency dependence, no omega terms there. The s to the 0 coefficient, which does not make me a rapper. So anything to the 0 is 1, yeah? My s to the this is a polynomial in s, and this is a polynomial in s. And it just so happens it's a polynomial of order 1. That's to say s to the 1 is the highest term. And that we must make sure we get 1 here. We can't have a multiplying factor through our polynomial. When you write, if you want to get the tau, the right value, this has to be 1 and this has to be 1. And you have to order your mathematics to make it so. And if you don't, you will get the wrong time constant, and I will laugh at you. Not publicly, obviously, just when I sit there looking at the scripts, I'll giggle. The other thing you should know is that the highest power of s is 1. There is no s squared on the bottom. If it was, it would be second order. For real systems which are physically realisable and obey causal laws, that's to say time progresses into the future from the past and not the other way around, or doesn't stand still, you can't have anything in the top, power of s, more than you've got power of s in the bottom. So if you did have a second order system, you'd have s squared on the bottom, and you'd have s squared on the top if it was high pass, s on the top if it was band pass, and 1, that's to say s to the 0, on the top if it was low pass. You cannot have s to the 3 on the top with s to the 2 on the bottom. Well, you can do whatever you like mathematically, but there is no physical circuit that can realise that system. And there is no arrangement of springs and masses and oil-filled dampers that can do it either. You can't do it mechanically. So this is the answer, and we're heading towards it. A good idea when you look at these circuits, first of all, is to just say, what's the high frequency gain, what's the low frequency gain? And you can do it without any maths. You just have to say, well, high frequencies, XC1 goes to 0, and low frequencies, XC1 goes to infinite. Where does that leave me? Well, if XC1 goes to infinite, R3 plays no part, and I should have R2 over R1 plus R2. Happy? And funnily enough, that's what K turns out to be. On the other hand, if F goes to infinity, this looks like short circuit, and R1 and R3 are in parallel with each other. And then we have a potential divider, R2 over R1 parallel R3 plus R2. Sorry, R2 over R1 parallel R3 plus R2. And we will see right at the very end, if there's a bit of time, that you can cross out the S terms and end up with that high frequency gain. It's a good sanity check. So this circuit is a potential divider with R2 developing the output voltage. That's to say, measure the output voltage across R2. So we've got R2 times Vin upon R2 plus R1 parallel R3 plus 1 over SC1. So we write that straight from the circuit. Happy with that? And then I will expand this power, because this is not real mathematics, it's engineer's mathematics. So we have to do R1 times that lot over R1 plus that lot, which is that point there. And the R2 stays the same, and I divide through by VI to give me the left-hand side. Happy? Each of the steps is simple. It's just making sure the order is proper. Now, we've got to get a 1 on the bottom because we need S something plus 1. And if we can't get that 1 on the bottom, there's no point in looking for the 1 on the top. It's not coming. And there's no point in trying to get the K because you won't get that either. You've got to get the 1 on the bottom first. In fact, we need 1 plus S tau on the bottom. So I'll multiply the top. Are we all right with top and bottom? I can't be doing with numerator and denominator. It's far too difficult to say. I'm going to carry on the top and bottom. I don't care. Multiply the top, which is the numerator, and the bottom, which is the denominator, by this bit here to get rid of it. So I'm going to end up with R2 times this lot plus this bit here on the bottom, and R2 times this lot on the top, which is that bit. Happy with that? All that's happened is this gone up there, multiply that, which is that bracket, and this stays on its own, just there, and then the R2 up the top multiplies that lot. Then I just expand the bracket, and I multiply everything out, and I end up with this business here. And I've got some terms in S, and I've got some terms in no S, or S to the 0 if you prefer. So I'm going to get rid of the SC1s by multiplying through by that, so I'll end up with SC1 times this one and this one, where I've taken out the R2 to leave me the R1 and the R3. So factorise this chunk by R2 to leave R1 plus R3 and multiply by SC1 to give that bit. Then I've got the R2 on its own because I multiply through by SC1, so the SC1 that appears here cancels with that one to leave R2. Then I have R1 times R3 plus SC1, which is that bit there, and that R1 loses SC1 because they cancel. And on top, I factorise the same as I did. Oh, I factorise slightly differently actually. Oh, I could have factorised out the R2. What an ass. Never mind, you can factorise that if you like. So I've got R1 plus R1 times R2 plus R3 times R2 times SC1 plus the R2, which that SC1 cancels with the SC1 that goes on top. Happy? Good. So I've got a unity term, that's to say a coefficient of S to the 0 in the denominator, which is R1 plus R2. It's that R2 there and that R1 there. And I've got to get rid of them because I need 1 on the bottom. And until I've got 1 on the bottom, all my S terms don't have the time constant attached. They've got the time constant and a factor, and it's that factor that needs to bugger off. So I will divide the top and the bottom by R1 plus R2 to get my 1. So I just shuffled this to that. So I divide all the S, expanded that, and put this in with it to there. Divide by that, and I take out the SD1 because it's part of them. I divide the R1 plus R2 by R1 plus R2 and get 1. Happy? And then on the top, I did factorise that then. So divide this chunk here, having taken out R2, by R1 plus R2, and I end up with R2 from here, divide by R1 plus R2 on top. So this business here, C1 times this bracket, divide by that, is my tau naught, time constant, 1 over omega naught. And I know it is because I've managed to get my 1. No 1, no time constant. The top, on the other hand, is not finished with because I've still got this R2 over R1 plus R2. And this cannot be my 0 time constant until this has gone to 1. So I've got to get rid of this somehow. I can't start dividing the bottom again because the bottom is in the form that I want it already. No more shuffling the bottom, it's not allowed. Even they agree. I'm going to read this. Having found the desired form of the denominator, we know the pole has a time constant of whatever that equation says. And the numerator is still not in the right form though, because we have to have 1 plus S tau 1. So we've got to divide the numerator by the numerator's present coefficients of S raised to the 0. In other words, we've got to divide it through by this bit here. We can't change the denominator because it's already in the desired form, so we will unbalance our expression. We're going to divide the top by something, and we're not going to divide the bottom by it, and that means our expression is changed. It's no longer the expression we started with. We mathematically fiddled with it, and we have to unfiddle with it to make it true later. And that unfiddling will be what becomes our K. So K will balance the top and the bottom in the end. And K will be the the frequency independent part of the gain. It will restore balance. I think I was going to make a joke about the force, but on reflection, I don't think I'll bother. So I divided through by R2 over R1 plus R2. This obviously drops to 1 because I divided through. And this R2, well, R1 plus R2 goes with that R1 plus R2 to leave R2 brackets R1 plus R3 plus R2. Happy that these two can go away and just leave the fraction. If you don't like it, multiply out by yourself and see what's what. And then I take out this because I divided through by it here and here. I have to multiply through by it later. And I can actually drag this right outside and put it here with a dot just there. And then I'll have a 1 just here. I can see that in the, oh, I didn't put it in the next slide. I just say that if you perform the cancellations in 17, it will drop to 10, where 10 is the original one. That one, where we've got the 1 there, and the R2 over R1 plus R2 outside. Happy with it? Yes?
Why hasn't that R2 after SC1, why hasn't the R2 been cancelled out? We've got R2 brackets R1 plus R3 over R2.
This R2?
That's the one.
So, very, very briefly, the only thing I'm going to do is introduce an op-amp. And the op-amp is all in all very happy with op-amps, they're our best friends. The only thing that's left now is just to do a bit of maths. And the method by which you do it is the same as analysed in any other circuit. So this one is non-inverting, just to show you a non-inverting one as well. And we would usually say, well, V minus is VL in the potential division of R2 and this lot. So I call it Z2 and Z1. And we can do the same thing with the high frequency and low frequency gain that we usually do and say if HF, or at HF, which is F tends to infinity, the impedance, sorry, that's strictly is wrong because I've got capacitance in ohms, which is a total lie. It's XC, you might like to change that, tends to 0, and we have R2 plus R1, if I'm calling all this R1, but I call it Z1 because there's a frequency dependent bit. So I've got Z2 plus Z1 over Z1, which is the regular non-inverting op-amp expression from 118, except I've thrown away R's and I put in Z's. There is no real difference other than that. Happy? In which case I can do the low frequency gain as well, where I say that F tends to 0, the impedance of C tends to infinite ohms, so R3 plays no part, and I end up with this bit disappearing, and I've got a non-inverting amplifier composed of R2 and R1, which has a gain of R2 plus R1 over R1, which is exactly the same as we see in 118. So I know that my expression is going to be Z2 plus Z1 over Z1, where I ringed up Z1 and Z2, and that's just because it's an op-amp circuit and I've generalised it into Z rather than just R. And I know that my expression will be R2 plus R1 parallel with that lot, because that parallel with those two, divided by Z1, which is that parallel with those two. Happy with how I get that? In which case, if I multiply through to undo the parallel signs, which are not real mathematics, I will end up with 21. And I've got to get back towards an S tau plus 1 on the bottom and an S tau plus 1 on the top and a K out the front. So I've got my R1 plus R3 plus 1 over J omega C. I did this one in J omega just in case you don't like tau. If you want to see one done in F, you'll have to write Excel. I'm not doing that too. This one is enough, I think. You just put 2 pi in, basically. So I'm going to multiply through by this term here, well, this term here actually, to yield. Am I? What did I do? I did, but well, I multiplied the top and the bottom by this first. So I did just as the J omega C bit. So I'll end up with 1 here, and J omega C R1 plus R3, which is that bit there, and I multiply the top by the top of the denominator by J omega C, so I get J omega C R1 brackets R3 plus 1, which is that bit there. And I do the same for the top. So that bit's the same as that bit. So that bit's the same as that bit. And then, have I missed something there? Anyway, assuming that's right, or I've unintroduced my mistake, that's why I don't like doing maths. You have to make sure everything's right. It's much easier to write it down on paper. You would then try to get rid of this bit here, 1 plus j omega CR1 plus R3, by multiplying top and bottom by that. So you get R2, perhaps with something here if I made a mistake or not, times all of this stuff which is in the bracket, plus the rest of this bit here without that underneath because it's gone, which leaves you that bit. And for the bottom we just have R1, R3j omega C plus 1, because this bit goes away and cancels with itself if you prefer, to yield 23. That's why I like to do things with S2. Gives you less stuff to write down, makes it much easier. Less things to make a mistake on. So if we collect up the terms, so I'm essentially collecting terms in S now, but I'm calling it j omega. So I've got some terms that are in S to the 0, and I've got some terms that are in S to the 1, and I've got some terms that are in S to the 0, which is R1, and I've got some terms in S to the 1, which is CR3, really. And I'm going to take out the R2, the R1, and that R1 to make my K. So taking K out and comparing the terms with the standard form, so I just compare this bit to that bit. F1 becomes this lot, which is really that fraction there, and F0 becomes 1 over that bit there. Well, I put 2 pi in at this point because it's F, and the K is that bit there. But this is how you would compare terms at the end. And you can do it with S as well, it makes no difference. So what about, I know I've run, what have you guys got next? Nothing. Sweet, well it's week 12, so there's nothing in here. We'll carry on for a bit. I'm nearly done. So what happens when f goes to infinity? Can you cancel stuff out and see? Well, if I take the magnitude of the transfer function, I will square everything, square the top and the bottom, and then root it. And that will give me a situation where at high frequencies, the ones don't count because f is getting really big. So f over something squared, big numbers. 1 squared, 1. But on the other hand, when f is very small, f much less than 1, there is somebody in here I think. We'll hurry up. F much less than 1, f squared, pretty tiny. 1 squared, still 1, quite big. So it will either be at high frequencies, the f's dominate, at low frequencies, the 1's dominate. So we can cross out the appropriate terms by getting rid of the c's and the 2 pi's and crossing out that and that cancel, that and that cancel to yield this business. And you can reshuffle them into this bit here. This is just some trickery with algebra, nothing else. Right, if you did the other one, you'll find that it tends to K. We'll have to stop because I think we're late.